welcome to Ether Demo 1. I will give you an overview of our testbed setup before we start showing the individual parts with screen recordings. So up here we have the ground segment virtualized in AMD 64 hardware. Then we have two satellites represented by our flexible payload hardware, which consists of an ARM processor, FPGA and SDR. So we have two of those. Now when we use the 3GPP cellular mode, we connect to Amarisoft eNodeB B frontends, and then we have the IF part wired up here with splitters and combiners to the user terminals, which run the semantics-aware information handling. Now the orchestration of ground and satellites, or what part on the satellite is running, the different applications with a flexible payload, is orchestrated here, and that's the overview of the orchestrator. Now on to the actual demo part with the screen recording.
Let's have a closer look at the orchestration and flexible payload operation. The orchestrator is based on open source MANO. We developed an extension that allows an operator to select a geographic region where one or more services should be active. When deployed, the orchestrator dynamically instantiates the service as a container on the selected satellite when it orbits over the selected area. In this example, a satellite orbits over the Iberian Peninsula. On the left side of the screen, we can see the spectrum visualization provided by a service. On the bottom right side, a list of containers that are running on the satellite is shown. One of the services is cellular IoT, and the first crucial operation is a UE attach. On the upper left side of the screen, the UE terminal is shown. On the lower left side, we can see the log of our satellite store and forward function. On the right side, the satellite's eNodeB B log is showing with S1 and NAS signaling messages. We start by triggering the attach procedure by rebooting the UE. The initial attach fails because authentication vectors are not yet available on board. Once the feeder link becomes available, pending vectors and subscription information is obtained from ground-based local or roaming HSS and transmitted to the satellites. The subsequent attach procedure succeeds using the retrieved subscriber information. The UE context is now created locally on the satellite, including identifiers, tracking area information, and NAS security context. Moving on to the user data transmission under store and forward operation. You see the UE terminal at the top left again, the PDN log at the bottom left, the satellite store and forward log in the middle, and behind that, the eNodeB B log. While the service link is available, we transmit a UDP packet from the UE to the satellite. The packet is encapsulated in NAS signaling and arrives at the satellite, where it is buffered by the store and forward function. Once the feeder link becomes available, the packet is transmitted to the ground segment, where it is forwarded to the PDN. Now, in order to enable seamless multi-satellite operation, the UE context is disseminated asynchronously. The satellite's context dissemination function log is shown at the top left side of the screen. Below that is the UE terminal, and on the right side is the satellite's eNodeB B log. At this stage, the service link between the first satellite and the UE is available. The UE has completed the attach procedure with this satellite and can transmit user data packets. Once the feeder link between the satellite and the ground segment becomes available, the UE context created at the first satellite is transmitted to the ground. And then it is transmitted to the second satellite during feeder link availability to this satellite. When the second satellite is passing over the UE, the availability of the UE context on that satellite allows it to seamlessly resume NAS signaling with user data transmission without the need of reattaching the UE. Drastically reduces the signaling overhead. Furthermore, the UE can continue to resume NAS signaling with the first satellite as well as it is shown here. The last part of the demo is the semantics-aware information handling. On the left side of the screen, the UE terminal is shown, which runs the containerized application. On the right side of the screen is the eNodeB B log of the satellite, where we will be able to see the reception of relevant messages. The system integrates semantics-aware transmission scheduling based on the version age of information. Only relevant updates are transmitted, reducing unnecessary signaling and improving energy efficiency. The mechanism is particularly suited for delay-tolerant IoT applications over non-terrestrial networks. We have pre-recorded temperature sensor readings from a real sensor in the field, which are being replayed in the system. As you can see in the log on the left, the first 3 messages are not being transmitted. Now the 8th message is considered relevant by the system and is being transmitted. At the eNodeB log, we see the service request message that contains the sensor reading encapsulated in the user data container of the NAS message. The sensor value is hex encoded. Now, after some time, the 16th sensor reading is also being transmitted. At the end, 19 messages were generated and 2 of them were transmitted, which is a reduction of 89% in transmissions.